If you're ready to fall asleep to the wonders of the universe, like how gravity shapes galaxies, or why light can act like a particle, this video is just for you. Let complex physics gently guide you into a deep, restful sleep. If you enjoy relaxing science stories like this, don't forget to like the video and subscribe for more sleep-friendly journeys through space, time, and everything in between. Newtonian mechanics is where the foundational story of modern physics takes root. It belongs to the classical realm of physics and is all about explaining how things move when forces act on them. Developed in the 17th century by Sir Isaac Newton, it became the go-to framework for understanding motion in everyday life. Think of it as the physics that governs why a thrown ball arcs through the air, or why planets orbit stars with clockwork precision. Picture this: you toss a ball. You instinctively know the arc it will follow. That intuition is grounded in Newtonian mechanics. From predicting when the sun will rise tomorrow, to mapping planetary orbits, or sending rockets to space, it all traces back to this system. At its core, Newtonian mechanics rests on a few deceptively simple principles, laws, that forever changed how humanity perceived motion and the universe. Let's begin with Newton's first law, often referred to as the law of inertia. It states that an object will stay at rest or keep moving in a straight line at constant speed unless acted upon by an external force. In other words, if you kicked a ball on an infinite, perfectly smooth surface with zero resistance, it would keep moving forever. Of course, that doesn't happen in real life because of friction and other forces. But in a frictionless vacuum, the ball would roll eternally. This idea was revolutionary. Before Newton, many thought objects stopped moving on their own due to some internal nature. Newton turned that on its head by showing its external forces that cause change, not some internal tendency. Objects naturally keep doing what they're doing until something else interferes. Now, Newton's second law is a game changer. This is the famous formula: F equals ma. Force equals mass times acceleration. It sounds simple, but its implications are immense. Imagine pushing a small rock and a heavy boulder. The same push won't move them equally. The heavier object needs more force to accelerate. This law allows scientists and engineers to predict how things will move under any given force. This isn't just theory, it's how rockets are designed, cars are engineered, and buildings are constructed to stand against winds and earthquakes. Want to launch a satellite into orbit or calculate how fast a plane can lift off? You're using Newton's second law. Then comes Newton's third law. For every action, there's an equal and opposite reaction. Push against a wall, and it pushes back just as hard. This principle is behind how swimmers propel through water and how jet engines thrust planes forward. A rocket firing gas backward moves forward by this very law. One of Newton's most iconic contributions was the universal law of gravitation. It asserts that every object in the universe pulls on every other object with a force. The strength of that force depends on their masses and the distance between them. Double the mass, double the pull, double the distance. The force drops to 1/4. This gravitational law wasn't limited to falling apples. It explained moon orbits, planetary motion, and tidal effects. It unified the heavens and the earth under one simple force. That concept that the same force applies everywhere was a radical shift in thought. Newton's gravitational model enabled astronomers to predict the movement of celestial bodies with astonishing accuracy. It also explained the path of a cannonball and the falling of a feather. Everything that moves under gravity's influence suddenly made sense. But the influence of Newtonian mechanics didn't stop with science. It affected engineering, space exploration, and our daily lives. Skyscrapers, airplanes, bridges of them owe their structural integrity to the calculations based on Newton's laws. Space travel, especially, would be unthinkable without these principles. Take space missions, for instance. Plotting the trajectory of a satellite or spacecraft involves understanding how gravity from various bodies will influence its path. Engineers map those forces using Newtonian equations. Even today, while advanced theories exist, Newtonian mechanics remains the go-to tool for real-world movement and design. That said, Newtonian mechanics has its limitations. It works wonderfully in most everyday situations. But it begins to break down when we explore extremes like objects moving near the speed of light or within powerful gravitational fields. In those cases, Einstein's theories take over. Likewise, when studying atoms and subatomic particles, quantum mechanics steps in. Newton's laws can't account for the odd behavior seen at microscopic scales. Despite these shortcomings, Newtonian mechanics is still a powerhouse in practical physics. It continues to provide incredibly accurate predictions for the vast majority of scenarios we encounter. Whether you recalculating how fast a car needs to go to clear a ramp or designing a roller coaster, Newton's principles are your guiding tools. There's a beauty in this simplicity. A handful of laws can explain everything from how a bicycle rolls down a hill to how the Earth orbits the Sun. Newton showed that the universe wasn't a chaotic mess, it was governed by rules, and we could understand them. And it all started with the idea that motion could be measured, predicted, and understood through clear, consistent laws. Newtonian mechanics may seem basic compared to modern physics, but its elegance, power, and reach continue to shape how we explore and interact with the world. Thermodynamics. Thermodynamics is the study of heat, energy, and the laws that govern their interactions. It applies to everything from engines and refrigerators to stars and human metabolism. This branch of physics helps explain how energy flows, how it changes form, and why some transformations are irreversible. It's a window into both the invisible mechanisms inside molecules and the vast operations of entire galaxies. At the heart of thermodynamics lies the concept of energy. Energy exists in many forms: kinetic, potential, chemical, thermal, and more. Thermodynamics explores how these forms of energy are transferred and transformed, especially through heat and work. It provides the rules that dictate what is possible in any physical system involving energy exchange. The first law of thermodynamics is a statement of energy conservation. It tells us that energy cannot be created or destroyed, only converted from one form to another. If you heat a pot of water, the energy from the burner transfers into the water molecules, increasing their motion. That motion is what we perceive as heat. The total energy remains constant. It just shifts from one place or form to another. This law underpins everything from running a marathon to charging a battery. In biological systems, chemical energy from food is converted into heat and movement. In power plants, fuel is burned to convert chemical energy into electricity. Every action and reaction obeys this unbreakable law of conservation. Then comes the second law of thermodynamics, principle that introduces the concept of entropy. Entropy is often described as a measure of disorder, but it's more accurately a measure of how energy becomes spread out or randomized. The second law says that in any energy transfer or transformation, the total entropy of the universe increases. This explains why heat always flows from hot to cold, never the other way around. If you place a hot mug on a cold counter, heat spreads from the mug into the counter. That transfer increases the system's entropy. Over time, systems tend to move toward greater disorder unless energy is input to maintain structure. Entropy reveals why perpetual motion machines are impossible. No machine can operate forever without losing useful energy to heat or friction. Even the most efficient engine wastes some energy as heat. This law defines the direction of time. It explains why you remember the past but not the future, because entropy increases with time, creating an irreversible arrow. One of the most dramatic implications of the second law is heat death, the idea that the universe will eventually reach maximum entropy. In that distant future, all energy will be uniformly spread, and no work will be possible. Stars will burn out, matter will decay, and the universe will become cold and lifeless. It's a sobering vision, but also a testament to how fundamental thermodynamics is. The third law of thermodynamics states that, as a system approaches absolute zero, the coldest temperature possible leads, entropy approaches a minimum. The zeroth law of thermodynamics may sound oddly named, but it's foundational. It states that if two systems are in thermal equilibrium with a third system, they are in equilibrium with each other. This is how we define temperature. It allows for the creation of thermometers and the measurement of heat exchange between objects. Together, these four laws shape every physical process involving energy. They're not just for scientists, they affect everything we do. Cooking food, lighting a room, fueling a car, and even growing a plant all follow thermodynamic principles. Your body is a living engine, taking in energy, using it for work, and releasing it as heat. In industry, thermodynamics is critical. Engineers design engines to maximize work and minimize waste. Air conditioners, refrigerators, and heat pumps all rely on understanding how to move heat efficiently. Thermodynamics even plays a role in computing where heat generation from microchips poses design challenges. In the cosmos, thermodynamics explains how stars shine. Nuclear fusion in a star's core releases enormous amounts of energy, radiating out as light and heat. That energy journey follows thermodynamic laws transferring through layers of plasma, losing some order and increasing entropy as it travels through space. Entropy also governs the collapse of stars into black holes. When a massive star exhausts its fuel, it can no longer resist gravitational compression. The core collapses and entropy skyrockets. Black holes are thought to have the highest entropy of any known objects in the universe. It's a paradox that's driving new theories in physics. In chemistry, thermodynamics predicts which reactions will occur. A reaction may be possible in theory, but if it doesn't increase entropy or release usable energy, it won't happen spontaneously. This guides everything from designing pharmaceuticals to understanding ecosystems. Thermodynamics also touches philosophy. The inevitability of entropy increase invites reflection on time, change, and the nature of life. Why does life seem to create order in a universe trending toward disorder? The answer lies in how living things absorb energy and export entropy. Life doesn't break, the second lot thrives within it. Even information has thermodynamic significance. The act of erasing data, for instance, increases entropy. In fact, some scientists explore the links between entropy and consciousness, suggesting that thought and awareness may have energy costs measurable by thermodynamics. Ultimately, thermodynamics gives us a universal lens. It connects the flicker of a candle to the glow of galaxies. It tells us why energy must flow, why time marches on, and why nothing stays the same forever. It offers laws that are simple in form, yet profound in consequence. As you rest tonight, know that the warmth you feel, the steady rhythm of your breath, and the gradual slowing of your body are all thermodynamic processes. You are exchanging energy with your environment. Your body cools slightly, releasing heat into the air. Molecules move, atoms vibrate, and entropy subtly increases. Everything flows from heat to light to thought. And in this great flow, thermodynamics is the map that shows us where we are and where we're headed. It's not just about heat, it's about existence. It's about why things happen and why they eventually come to rest. So let your thoughts quiet. Let the warmth of understanding settle in. You are part of a universe guided by energy, movement, and change. And as the laws of thermodynamics unfold quietly around you, may they bring both wonder and peace. Electromagnetism. Electromagnetism is the force that governs electricity, magnetism, and light. It's one of the four fundamental forces in nature and explains how particles with electric charge interact with one another and with magnetic fields. From the glow of a light bulb to the pull of a magnet, this branch of physics illuminates how much of our modern world works. It all begins with electric charges. There are two types: positive and negative, and opposite charges attract while like charges repel. The behavior of these charges is governed by Coulomb's law, which quantifies the force between them. The greater the charge and the closer they are, the stronger the force. This principle is similar in form to Newton's law of gravity, but much stronger and with both attractive and repulsive properties. Electric fields surround every charged object. These fields extend outward and exert forces on other charges that enter them. The concept of a field revolutionized physics. Instead of thinking of forces acting across empty space, fields provided a way to describe how space itself becomes energized around charges. Then there's current, when charges flow, usually through a conductor like copper wire. This movement of charge is what powers electronics, from smartphones to refrigerators. The flow of electrons is driven by potential differences, or voltages, and governed by Ohm's law. V equals I. Voltage equals current times resistance. Magnetism is deeply connected to electricity. Moving electric charges create magnetic fields, and changing magnetic fields can induce electric currents. This interplay is captured in Faraday's law of induction, which is the foundation of how generators and transformers work. Spin a coil of wire in a magnetic field, and you create electricity. Maxwell's equations unify electricity and magnetism into a single framework. These four equations describe how electric and magnetic fields are generated and altered by charges and currents. They also predicted the existence of electromagnetic waves, disturbances in electric and magnetic fields that travel through space. Light itself is one such wave. Electromagnetic radiation spans a vast spectrum, from low-energy radio waves to high-energy gamma rays. Visible light is just a small slice. These waves all travel at the speed of light in a vacuum about 300,000 kilometers per second. The discovery that light is an electromagnetic wave was monumental. It connected optics, electricity, and magnetism in one elegant theory. It explained reflection, refraction, and interference. Suddenly, light wasn't just something you was a measurable, predictable phenomenon. Electricity and magnetism also enable technology. Electric motors convert electrical energy into mechanical motion. Generators do the reverse. Radio signals use oscillating electric fields to carry information through the air. MRI machines use strong magnetic fields to look inside the human body. This force is also essential to chemistry. Electromagnetic interactions hold atoms together. The structure of atoms. Without electromagnetism, atoms couldn't exist, let alone molecules, solids, or life. Even the sun shines because of electromagnetism. The energy generated by nuclear fusion travels outward as electromagnetic radiation. It bathes Earth in light and heat, making life possible. Solar panels capture this energy and convert it into usable electricity. As powerful as it is, electromagnetism behaves differently at different scales. In large-scale systems, fields behave classically smoothly and predictably. But at atomic scales, quantum mechanics enters the picture. The electromagnetic force is responsible for the structure of the atom and the behavior of light at the quantum level. In modern physics, electromagnetism is understood as being mediated by photons, massless particles that carry the electromagnetic force. Quantum electrodynamics, or QED, is the quantum theory that describes these interactions with stunning accuracy. This force governs not only the devices we use daily, but also the fundamental structure of matter. It's responsible for the visible universe and most of the processes we interact with. From thunderclouds to touchscreens, from X-rays to Wi-Fi, electromagnetism powers it all. So next time you flip a switch, charge your phone, or feel the warmth of sunlight, remember that electromagnetism is quietly at work, orchestrating the flow of energy through the universe. Relativity. Einstein's theory of relativity redefined our understanding of space, time, and gravity. While Newtonian mechanics works well for most everyday situations, it begins to break down at very high speeds or in strong gravitational fields. That's where relativity steps in with two theories: special relativity and general relativity. Special relativity, proposed in 1905, focuses on observers moving at constant speeds, no acceleration. It starts from two simple but powerful postulates. The laws of physics are the same for all non-accelerating observers. And the speed of light is the same in all directions for all observers, regardless of their motion. These ideas lead to mind-bending consequences. Time slows down for objects moving close to the speed of light, a phenomenon called time dilation. Lengths contract in the direction of motion, and mass increases with speed. All of these effects have been confirmed experimentally, especially with high-speed particles in accelerators. Special relativity also introduced the iconic equation E equals mc. Energy equals mass times the speed of light squared. This means that mass and energy are interchangeable. Even a tiny bit of mass can yield enormous energy, an insight that powers nuclear reactions and explains the energy output of stars. General relativity, published in 1915, extends these ideas to include acceleration and gravity. Einstein proposed that gravity isn't a force between masses, but rather the warping of space-time itself. Massive objects curve space-time, and other objects move along the curves. This replaced Newton's view of gravity as a force acting across empty space. Imagine placing a bowling ball on a trampoline net, bends the surface. Now roll a marble near it. The marble curves around the indentation. That's how general relativity describes planetary orbits and the bending of light by massive objects. One of the most stunning confirmations of general relativity came during a solar eclipse in 1919. Starlight was observed bending around the sun, just as Einstein had predicted. Since then, relativity has been tested and confirmed countless times, including by GPS satellites, that must account for both special and general relativity to provide accurate positioning. Relativity also predicts black holes' regions where space-time curves so intensely that not even light can escape. These enigmatic objects were once theoretical, but are now observed through gravitational waves and X-ray emissions. They offer a glimpse into the extremes of the universe. Time itself behaves differently in strong gravitational fields. Near a black hole, time slows dramatically. This is called gravitational time dilation and has real-world applications, such as in the synchronization of satellite clocks. Relativity redefines our understanding of the cosmos. It connects space and time into a single entity's space-time. Man shows that the universe is not a static stage, but a dynamic, flexible fabric shaped by mass and energy. Though relativity is complex, its predictions are elegant and consistent with observation. From the orbits of planets to the functioning of atomic clocks, it governs the structure of space and the flow of time. With relativity, Einstein didn't just rewrite the rules of physics, he revealed a deeper, richer reality. One where time bends, light curves, and the universe itself is constantly evolving. Quantum mechanics. Quantum mechanics is the science of the very small, the rules that govern the strange, often counterintuitive behavior of particles at atomic and subatomic scales. Unlike classical mechanics, which deals with the predictable motion of objects we can see, quantum mechanics explores a world that defies common sense. It all began in the early 20th century when scientists noticed that classical physics could unexplain certain phenomena. One major puzzle was black-body radiation, the way objects emit light when heated. Classical theories predicted an ultraviolet catastrophe where energy would become infinite at short wavelengths. But experiments didn't agree. Enter Max Planck. Planck proposed that energy isn't continuous, but comes in small packets called quanta. This led to the idea that light, usually thought of as a wave, also behaves like a particle of photon. Einstein took this further by using quanta to explain the photoelectric effect, where light knocks electrons off a metal surface. His work proved that light has both wave-like and particle-like properties. This duality became a cornerstone of quantum theory. Particles, such as electrons, don't behave like tiny billiard balls. They act like waves too, capable of interfering with themselves in a double-slit experiment, producing patterns of light and dark that indicate wave behavior. But quantum mechanics didn't stop at wave-particle duality. Werner Heisenberg introduced the uncertainty principle. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This isn't a limitation of technology, it's a fundamental feature of nature. Then came Schrödinger, who developed an equation that describes how quantum systems evolve over time. His famous thought experiment, Schrödinger's cat, illustrates how particles exist in multiple states at once, called superpositioning till observed. A cat sealed in a box with a quantum-triggered poison is both alive and dead until someone looks inside. Another strange feature is entanglement. When particles become entangled, the state of one instantly affects the state of the other, no matter how far apart they are. Einstein called this spooky action at a distance, but experiments confirm it. Quantum entanglement now powers advances in cryptography and could lead to ultra-secure communication. Quantum mechanics forms the foundation of modern technology. Lasers, magnetic resonance imaging, and even solar panels all rely on quantum principles. At the heart of quantum theory is probability. Unlike classical physics, where outcomes are deterministic, quantum mechanics only predicts the likelihood of an event. This randomness is baked into the universe. The wave function, a key concept in quantum mechanics, describes a cloud of probabilities rather than exact paths. As we probe deeper into matter, we find a zoo of subatomic particles, quarks, leptons, and bosons. Quantum field theory, an extension of quantum mechanics, describes how particles arise from underlying fields. The most successful of these theories is the Standard Model, which unites three of the four fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. Despite its success, quantum mechanics remains puzzling. Interpretations vary. Some say the wave function collapses when observed. Others suggest all possibilities play out in parallel universes, the many worlds interpretation. There's no consensus, but experiments continue to support quantum predictions. We now stand at the edge of a new era: quantum computing. These machines use qubits, quantum bits, that can exist in multiple states at once. They hold the potential to solve problems too complex for classical computers, revolutionizing fields from medicine to logistics. Quantum mechanics reshapes how we understand reality. It shows us a world where particles blink in and out of existence, where cause and effect blur, and where observation itself changes the outcome. It's unsettling, but also breathtakingly beautiful. Every time you use a phone, access the internet, or even heat something in a microwave, you're benefiting from the strange, invisible rules of the quantum world. It may be bizarre, but quantum mechanics is the most accurate, experimentally tested theory in all of science. It unlocks the secrets of atoms and opens the door to the future. Cosmology and the universe. Cosmology is the science of the universe, its origin, structure, evolution, and ultimate fate. It seeks to answer the biggest questions. Where did everything come from? What is the universe made of? How will it all end? Using physics, astronomy, and deep observations of the cosmos, cosmology paints a picture of reality on the grandest scale. At the heart of modern cosmology is the Big Bang Theory. It posits that the universe began around 13.8 billion years ago as an incredibly hot, dense point. Then it expanded and is still expanding. Evidence for this comes from the redshift of galaxies, which shows they're moving away from us, and from the cosmic microwave background, a faint glow of leftover radiation from the early universe. This radiation, discovered in 1965, is a snapshot of the universe when it was just 380,000 years old. It confirms predictions made by the Big Bang model. Tiny fluctuations in the CMB reveal the seeds of galaxies and galaxy clusters, showing how structure emerged over billions of years. Cosmologists study not only galaxies, but the vast voids between them. The universe forms a cosmic web, filaments of dark matter and gas stretching across unimaginable distances. Galaxies are like tiny nodes on this massive structure. And then there's dark matter. Observations of galaxy rotation and gravitational lensing suggest there's more mass than we can see. This unseen mass, called dark matter, makes up about 27% of the universe. Though invisible, it exerts gravity and helps bind galaxies together. Even more mysterious is dark energy. Discovered in the late 1990s through studies of distant supernova, dark energy appears to be accelerating the universe's expansion. It makes up roughly 68% of the universe. We don't know what it is, but it dominates the cosmos. Only about 5% of the universe consists of normal matter stars, planets, and people. The rest is a mystery, yet we know it exists through its effects. This humbling insight reminds us how little we truly know, even as we measure and model the universe with growing precision. Cosmology also explores the fate of the universe. Will it expand forever? Will it slow, stop, or reverse? Current data suggests continued expansion, leading to a heat death where galaxies drift apart. Stars burn out, and energy becomes evenly distributed. The universe would become cold, dark, and still. But other scenarios exist. If dark energy changes over time, it might tear everything apart. A big rip, or quantum effects might trigger a collapse, the big crunch. Some even theorize a cyclic universe, expanding, collapsing, and rebirthing in endless loops. The universe's structure isn't just out there, it's in us. The elements in your body, carbon, nitrogen, oxygen, were forged in the cores of ancient stars and spread by supernova. In a real sense, we are made of star stuff, as Carl Sagan once said. Telescopes like Hubble and the James Webb Space Telescope peer deeper into space and time, revealing galaxies as they were billions of years ago. Every photon they capture tells a story of cosmic history. Future missions may detect gravitational waves from the early universe or map the mysterious dark components with greater clarity. Cosmology bridges the largest and smallest scales. It connects quantum fluctuations with the formation of galaxies. It unites the physics of the atom with the birth of time and space. And it inspires us to ask profound questions about existence. In the stillness of night, when we gaze at the stars, we're not just looking at distant lights. We're witnessing echoes of creation. Light that began its journey long before Earth even existed. Cosmology tells us that the universe is vast, ancient, and evolving, and that we are part of its story. So, as you drift off to sleep, remember, you are connected to the cosmos in every way imaginable. From atoms born in stardust to thoughts shaped by light, you are a piece of the universe reflecting on itself. Reflections and final thoughts. As our journey through the landscape of physics draws to a close, let's pause and reflect on what we've explored. From the predictable rhythms of Newton's laws to the bewildering truths of quantum mechanics, we've traveled across scales from the cosmic to the subatomic. We began with motion and force, building a foundation with Newtonian mechanics. These principles taught us how objects behave in our everyday world, how to send rockets skyward, and why the Earth orbits the Sun. Then we stepped into the realm of energy with thermodynamics, understanding the relentless march of entropy and the power behind engines and ecosystems. Next, we unraveled the tapestry of electromagnetism of force woven into every light bulb, screen, and heartbeat. We saw how electricity and magnetism dance together, giving rise to waves of light and tools of modern life. From there, we shifted into Einstein's universe where space curves, time stretches, and nothing can move faster than light. Then came the quantum world, where certainty gives way to probabilities and particles defy intuition. It's a place where observation changes outcomes and reality itself seems flexible. And finally, we expanded outward into the cosmos, discovering a universe born from a fiery beginning, filled with mysteries like dark matter and dark energy. Through all these topics, one theme echoes: the universe is both understandable and mysterious. Science has provided remarkable insights, yet countless questions remain. We stand at the edge of knowledge, always seeking more. Let this thought bring you comfort as you drift to sleep. The same rules that guide the stars also shape the cells in your body. The same equations that describe black holes help explain your phone's touchscreen. You are part of a universe that follows elegant laws that humans, curious and persistent, have worked to reveal. Close your eyes and imagine the cosmos, the hum of distant galaxies, the rhythm of electrons, the curve of time. It's all connected, and you are in the middle of it, a quiet, thinking spark in a vast, unfolding story. Sleep well, dream deeply, and remember, the universe is still out there, full of wonder, patiently waiting for your next question.